no doubt. Did you do exercises in that regards with such type of questions?
Not a lot, because
Not a lot, probably.
I
Yeah.
did not have enough time.
Yeah, exactly. Yeah, I think with some exercise you will manage. No problem. It's like say at least typical, right? The chance of passing is whatever 50%, obviously in that case. And if you have how many, what is the probability of at least 3 people, 2 people, 5 people, whatever, right?
Yeah.
Yep. How, just to ask right now, Chris, and when you hear the word at least, what does that mean for you in terms of probability calculation?
It means that I have to take into account the value mentioned, and also the ones above it.
You're right. Okay. So, and what do you do then?
Um, so I think we first find the way, the amount of ways that wait, I don't know.
Yeah, it's exactly right. It's once you see it, it's quite clear what you have to do, but until you see it, it's a bit of a trick um, to realize the steps, right? So, well, yeah, of course, we're not going into math today, but just to do, if you do these exercises, then I think that will help a great deal. And these at least questions, they guaranteed always show up in a test. I mean, that's 99.9% probability that such kind of questions will show up. And the other, so at least this one. So, and typically you may have, did you have any arrival questions, say that a parcel or a delivery should take the probability of a delivery takes place at a certain time, and then something like what is the chance that you get the parcel within a week with at least 80% of the time you get it on time, when the individual event has a certain probability on its own. Did you deal with such questions?
Is it like a normal distribution or?
Not this one. It's a good point. Yeah, this one is the Poisson. But the normal distribution is then because it's a digital event. Also, in other words, it's either on time or it's not on time.
Oh yeah.
That's the big That's the big difference to the normal distribution actually. Then you can just p and the probability and the number of events along the lines of that. It's a good, and for the normal distribution, did you have to calculate the Z value so that you can utilize the standardized normal distribution, but for a specific, so that you get the probability from the standardized distribution table, but of course you have to apply to your specific problem, for which you have to calculate the so-called Z value. Right? Okay. Did you have such a question in the test?
Yeah, I think. Yeah, I had one or two.
Okay. Okay. All right. Okay. And was it okay for you to handle it, or?
Because I only I memorized the equation and how to use the table, so I just did it, but I don't know if I did it correctly.
If it was right or wrong. Okay. Okay. I mean, this one is that one you will most likely use all the time, again and again, in various, I mean, at uni most likely as well. The moment you have some data and you can fairly assume it's a normal distribution, then you very often apply exactly what we just discussed right now. So do you know somehow what is the idea behind that Z value? and the standardized normal distribution?
I know that you use the value, the mean, and the standard deviation to find.
Yep.
You can calculate the probability of the value.
Yeah, the one you're looking for, exactly. Yeah, that's a good point, right? I mean, let me just very briefly, when we look at the normal distribution, right? You have the bell curve, something like that. And of course, the average like this. And of course, ultimately it will be. So, what is the probability that something happens at all? It's a very strange question, but what is the probability of anything happening, so to speak, with that distribution, like with any other probability?
One.
Well, exactly, right? So that's always a good starting point to keep that in mind. And the specific thing, of course, ultimately it has a value where you hit the line, of course. So that is that little party will, of course, ultimately hit the line. When I'm here, what is the probability, or what is the accumulated probability value up to here, from basically infinite to or minus 3.3 up to this average value?
0.5.
Yeah, exactly. Huh? So the point is, it's very symmetrical, right? So it clearly cuts it in half, hence it's the average. So you have 50% of the event happening on this side and 50% of the event happening on that side, or some properties like the height of students in year 7, for example, of the boys, for example. Then there's an average, and then you can say, well, 50% of the students will be below the average and 50% above. That makes quite perfect sense. And then you have this far outreach, so to speak, at the far end. So the ones which are far below or the ones which are far above. That's the same for the which is ultimately a probability, right? That we say, what is the probability that one student is, if the average is, say, 160, that the student is 170, for example. That's where you can bring in these Z values, because the probabilities are always the same. They don't change. That's the key part of the normal distribution. But of course, if you have a value of, like what I just said now, 170 here, 160, and you have a certain sigma, here, one on this side and one on that side. Of course, for your very specific problem, you have a very different sigma. That's why you have that situation where you say, well, I'm looking at a problem, still Gauss, still normal distribution, where the average is 0, and that one, the sigma is 1. So that means when you go 3 times the sigma to the right, or 3.3, something like that, you see that you can look into one standard table, and you can clearly see, if I take the average plus 1.1 times sigma, so average plus sigma, that's the probability of that is, for example, 0.6 something, whatever. So that's in the table. You can check it out. Somebody, Mr. Gauss, originally went to all the pains to calculate that, of course, without a computer. And now the beauty of that, of course, you have it in the computer these days, in the notebook, in that calculator. But you can actually look into a table and check it out there of one specific point here with a certain distance to the center, meaning the average. That may be 2.45. And then you can say, what is the chance of average plus 2.54 times the sigma, which is obviously 1, to have a value up to here, a value below or above, then you can either do 1 minus or this one. And in order to do so, you have to shift your actual values. That's where the Z value comes into play, from the actual value you calculate into the so-called standardized normal distribution, which enables you then for the Z value to check it in the standard table, like what I just said, because otherwise you have to say, well, okay, I have here now, for example, 167.5. There's no table, of course, existing for that probability. That's but the probability for exactly the same position in the standardized one is existing. And that one may be 0.85 or whatever then the value is. Can't recall it from heart by heart. So that's why you transfer that value into this one and this one, sigma, into that one. Then you can really just check it out in the table what the probability is by transforming your specific problem into the standard problem. And in the standard problem, you can always check the probability, which, if you want to say so, is at exactly the same location, because in both cases, you have a normal distribution. So these two positions are then, so to speak, identical. And here you can calculate or actually look up at the table what the probability is. And because it's normal distribution, hence the same probability applies for your specific problem as well. So just this one is usually very helpful, because if you encounter that problem again and again and again, so the more natural it is to you, the better it is then. Huh? Okay, but I think that at least that is probably more the issue, because this one you can kind of standardize in the procedure. That's why I went a bit more into the details, a bit to look at the principle, not just the procedure is quite straightforward in the end, right? So that should always helpful to make some good marks. Whereas the at least that needs some better understanding exercises in order to solve it all the time. It's a bit less bit of a formula. Okay, so going back to I think we probably did the last time for the time being with the linear momentum. And before we start for today, because now we deal with some hard questions. What topic are you dealing with in physics now, Chris?
The significant like figures, and also the error.
Okay, yep. Well, that goes a bit together with the error calculation. Do you want to do something with that one next time, or is that okay and leave it aside?
I think we could do it next time.
Okay, all right, okay. Now have that ready for next time. That's good. Okay, all right, okay. So today, because typically in the test, it goes medium and hard. So that's why we deal today. Last time we did some medium. You can see it's typically then obviously always more related to angles or different particles in order to calculate, including angles. So that's typically when you move into the so-called hard level. So we want to, if you have that situation, fragments, that may be particles, electrons, photons, whatever, they travel in different directions, have different velocities, and we want to calculate the speed. And that's why look, we have to the speed of the fragment b.
I think first we could find the horizontal.
Yeah, that's a good approach. Yep. Always go with the horizontal or vertical. All right, okay. So what would be the horizontal momentum of A, so PA, speed?
First write the 3/2 m.
Yep.
And then times 1.2 v cosine 90 minus theta.
Okay, so what would that result in? I mean, when you think of the 90 minus theta cosine, what could you then transfer it to? Yeah, exactly. Yeah, good. That's good. Yep, sine theta, exactly. Yeah, a good one. That's why those basic issues always show up again and again from trigonometry and cosine, sine, these relationships in more complicated problems. That was just the foundation in the past. Okay, good. What about B?
Uh, 1/2 m times VA. I mean, wait,
So VB, yeah. Yep, no problem.
VB sine theta.
Yeah, exactly. Yeah. Okay. What about C? Any momentum from C? Because we talk about horizontal.
Yeah, it's the just 5/2 m times 0.6 v. I mean for the vertical, but in the
Yes, that's correct. Yep.
horizontal,
so horizontal
is 0.
0 exactly. Makes life a bit easier, right? By not having that to include. As you can see, obviously from that one, question 1C, is that probably a bit more complicated. But the principle is just it's starting to multiply in terms of how many particles you have to create the momentum. But the principle, of course, remains the same. Okay. So now how do we use the principle of conservation now for the horizontal one?
They should be equal.
Okay.
And, so I think we just write the PA equals PB.
Okay. And what can I say therefore? I mean, it goes both ways. Oh, let me say this is fine what you have. But I wanted to say is you could as well say, come from the side and say, well, PA means PB is 0. It depends sometimes on the question, right? Of what is more useful for what you're doing. Exactly. So I mean, one leads to the other. That's very obvious. But sometimes the other one is more helpful. Okay. So then, of course, we of course can utilize the equations we've set up. That should be VP, actually. So I just write it down. So when we have 3/2 and half v sine theta is half okay, and obviously that's sometimes again helpful. We want to know VB. Huh? So how do I solve? What do I get for VB? I mean, how do I solve it for VB?
So first moving the 1/2 m over by dividing, using it to divide, and I think we get the 3/2 m. The m gets cancelled out and the 2 cancel out, so it's just 3.
Exactly. Yep. So in other words, like 2/1, right?
Yeah.
And then is out. So okay.
And
then we have skip.
I think sine theta can be cancelled out.
Yeah, that's the beauty, right? Exactly. So basically, what we can always do is at that stage, for example, say I only have products, no sums or subtractions. So then, of course, I can start to eliminate, right? And say, okay, m, sine, sine, for example,
Yeah.
or half, half, right? I can come from that one as well. Okay.
Then
Oh, I missed that one for the time being, right?
I think we still have
Yes, half the left. Yeah.
yeah.
Thank you.
Wait, and also
Okay.
the 3 over 2.
Yep, the tree is the tree. Oh, the tree is left and the half is left. Exactly. It depends on how you go for it. Exactly. So what we have is like 3 half. Yeah. Make it a bit nicer. 3 half. No, wait a minute. Something. No, just tell me again, because I think something.
So 3 over 2 v equals v.
Yep. Exactly. So we have that one was a bit too hard to rush. So we have 3/2. Keep it simple. Exactly. We said we are going to eliminate the m's.
Oh wait,
halves.
wait, because I think we wrote it wrong because
Yeah, okay.
1.2v.
Ah, yeah, exactly. Thank you. Oh, suddenly 3/2 m times 1.2v sine exactly is half m sine. Okay, so then we can go to this. All right, then next one, of course, you can eliminate half as well. If we want to do that, I mean, from this one, same thing. Doesn't matter if it's a rational or an integer. Okay. Then you have 3 times 1.2. V is VB. Okay, is that okay?
Yeah.
Okay. We say 3.6 probably. 6V is VB. So basically, as you can see here, with a lot of when we do the elimination early on in a good way and correct, of course, then we simplified the whole thing tremendously because basically everything falls away. Then you have already easy. The right hand side is already what we want because everything half m sine was gone. So we just have VB left. That makes life obviously a bit easier. We don't even have to do any calculation, so to speak, by moving something over. Okay, good. Let's now we look into firework. Huh? That's quite often. The velocity v2, huh? So we want to know v2. So this one, huh? That's v2 for the first question, and 3 for the second.
So because the 4 and 2 fragment is in the same axis, so then for the momentum of 4 equals to momentum of 2.
Okay. And how? But okay. All right. Okay. Yes. So, what about 1 and 3? Sorry. Now I was one too many. Excuse me. My bad. So Okay. So when we go back, I want to 1b here. So to the angle theta, right? Now we still want to calculate the angle theta. How could we do that? It's a bit more math than anything else, but how could we do that? Because we need to do it with the physics approach in order to get the angle. So it's not as simple as it seems at the very first one. What would you choose in order to calculate the angle? And like they say, use the principle of conservation of momentum. So that's a hint, which is, of course, in a test eventually then missing. It's maybe then just saying determine the angle theta, right? But without the use the principle. But now it still states it. So how do you use the standard approach? We can say that like that as well, actually, in order to get the angle, which is a bit unusual. Standard approach, but we want to calculate something which we usually, well, we rather look at M and V, they set the angle. So how can we still use the standard approach to calculate the angle?
I think we could use the sign to calculate the vertical
okay, yeah. Okay. Good approach. And before we go into the details, just what has to be equal in terms of momentum without explicitly saying the calculation of the momentum at the first stage. So what has to be in balance, so to speak, or conserved?
The sum of vertical component of the momentum of A and B equals to momentum of C.
Okay, all right. PA plus PB, always in the vertical, of course, like you said. PC, huh? Exactly. So what is now a bit, how about the direction of the momentum? Because that sometimes suddenly leads to confusion, right?
The opposite direction.
Right, and so that's why we can say like what we say, right? So sometimes suddenly then, because we say this is going vertical, so this is obviously this part we are looking at, this part we are looking at, and obviously this part. So one is, so we have to introduce directions, right? But because they are equal, so we can operate, or let me rephrase that and say, sometimes in this context, it's maybe better to think of the direction because the sum of the momentums must be zero, right?
Yeah.
So we can, because, or why does it have to be zero before? Why is the momentum before zero?
Because before the explosion, I think it's stationary.
Yeah, I mean, there's exactly right. There's no momentum existing exactly. So that's a good one. So before is actually zero. So we can already go like this, and afterwards, of course, then we can go into the direction, right? Because then we can say, well, PA plus PB and minus PC, they must be equal. So that comes this one before and after must be zero. So that's one way where we can basically write, avoid a bit the pitfall of the direction, because sometimes it happens then that students say, okay, this is plus, so plus, plus, and this is minus, so minus. certainly we have a minus PC on that one, which is of course not correct, because then you would have PA plus PB plus PC equals 0. That can't be, because this is the right way in terms of direct shift. So that's why sometimes in the context with these explosions, fireworks stuff, rather to think, okay, before and after, before was 0, after I just go with my direction, plus, plus, minus. Then, of course, automatically this one comes into play, and there's no potential problem with suddenly a minus here, because I think this is minus. So I make a minus, which would be wrong. Okay, that's the key part, right? After that, it becomes an issue of just, of course, what is PA vertical, what is PB vertical, what is PC vertical. That one, of course, is obvious. And just quickly, nevertheless, just what is PA vertical?
I think we use the one. Wait, use first the 0/2m.
Yep.
Times 1.2 v sine theta. But cosine.
Cosine, exactly. Yeah, yeah. Like you had it before, right? I mean, one thing is you can say if in this there, and of course they make the theta on purpose here, so that it becomes a bit more tricky, that students have to think more about. Otherwise, it's just very obvious if that would be the angle, then sine, of course, is here. So they make it a bit more complicated by having theta here, so that you have, I mean, for the horizontal, excuse me, it's the wrong way around. So for the horizontal one, if this would be here, then of course it would be very clear cosine, but we have the angle here, so it's a bit different. So as we have then identified this one, right or wrong, then of course the other one must be the opposite, right? Of course, it's still a good time to rethink, is that really cos? But if we conclude for whatever reason, no, that should be sine, then the other one must be cos. So this is the cross check when we talk horizontal, vertical, right? To take that into consideration. Okay, so we have cos theta. Of course, the same applies for PB, just with a bit slightly different value. And of course, we have PC is obviously without any angle. And let's just write down PB, because the key for the ultimate solving of it is times VB, which we have now, okay, now we have it, so we can say 3.6 V cos theta. And when you look at the equation here, PC is obvious. So, and I want to solve it obviously for theta. So how can I solve the problem in order to get the angle, or rearrange the equation to get the angle?
And take PC and put it on the other side. Wait, yeah.
Yeah, okay. So we can go this way, right? That's fine. We just say we put PC on the other side. Then of course we can already eliminate probably some 5/2. So everybody's half. M is gone. V is gone, of course. So, and when we do this, I just write the whole story, so to speak. Equals 5/2 and 0.6. Yeah. So, what do you suggest me to eliminate, Chris?
M and V.
N, okay. And V, I can eliminate if it got been written there. Okay. All right. So we basically have left 3, 1, 5, right? Of course, the respective fraction. So what about the angle now? Oh, one more. Sorry, Chris. One more. You can actually eliminate the half as well, right? Maybe you mentioned it.
Yeah.
Because everything's half, right? So
yeah.
Strictly speaking, you would take it out first and then, but yes, okay. So to get the angle.
I think we like times the number first. So I think the left side we just directly because both is 3.6, then we can add them together.
Ah, okay.
So 7.
It's a good point. It's a good point, but ultimately it won't really help you to solve for cos or for theta, I mean. Right? So you want to get, in the end, you get some equation or of course, ultimately number, a numeric value. And when you look at it, you have something here with cos, something here with cos. So, and you're interested in cos. That's why it's highlighted. So this is what you're interested in. So how do you rearrange that side, first of all, in order to come to the solution for theta?
Like add them together, or
yes and no. Yeah, you can. Yeah, okay. If you follow that thought, you can add it together. How do you achieve that for the left-hand side? Well, what do you have to do as a first step to add the values together?
We get 3.6 cosine theta plus 3.6 cosine theta.
Okay. So in this case, of course, so you can add it up. That's where you followed, right? And of course, then you get the value. What I wanted to drive at was something else, because this is not so complicated. So of course, your approach is correct. You could just add them up and you get 7.2 divided by 3. So in that regards, it's then quite straightforward. But if you would have a more complicated equation, then you could say, I'm interested in theta, right? So that's what I want. So actually, I isolate it. Here it's a bit, yeah. In other words, you can take out the cos theta and then say 3. Of course, it's a bit too simple, but 3.6 plus 3.6. So in other words, you have what you are interested in isolated. Of course, here it's now just numeric value. So, of course, your approach is right now the better and the faster and the more simple approach. Just add it up. Then, of course, you can divide that and you get it. But if it's more complicated, then you can say, well, even so, I just both are something, maybe something more complicated at the front. And it may not even be identical for some reason. Then you can at least say, okay, maybe one still contains a v, the other one doesn't. But for whatever reason, right? Then you can say, well, I take out the cos to the front, and then everything, of course, is easy. Then I just have, of course, the situation where I have equals 3. You know what I mean, Chris? Oh, it's fine. So what I wanted to do is to say, well, as I'm interested in cos, so I take that out from the two, it's because it's sums, right? So whenever you have sum or subtraction, look at what you're interested in and then put it to the front, so to speak. Again, here, of course, it's very easy. I just have 3.6 cos plus 3.6, 7.2 cos. But if it would be more complicated, not just 3.6, but maybe still a certain equation, a certain unknown value, maybe you have something with A and B for whatever reason, it's maybe some other factors involving it, then you cannot just add them up. and you will not have a final value, of course. We'll just have an other equation where cos theta is expressed as an equation. Then you just take that one out, the one you're interested in. That's something which is quite often getting forgotten. It's like, oh man, what do I do now here with that? Then of course it's like, yeah, I just take that to the front. Then I come from something added up, also from a sum. I come kind of into a product. Huh? Then of course whatever is inside here, now it's still a sum, but it could be more than that. It could be a complete equation. Is separated from the one you're interested in. So it's a product of whatever is this here times the one you're interested in. Then, of course, you can just divide this one by that value here.
Yeah.
And you get cos theta. And, of course, then you make the inverse. Okay. All right. Good. Now, with this, so in order to V2, like you said it before, so I just go back. So we want to know V2, right? And for that one, you said they are equal. Huh? So would you even have to consider any angles?
No.
Exactly. Huh? So that's a good example where you actually change your coordinate system, so to speak, and you put and say, this is my coordinate system. I don't have to follow. And you see, some students will be misled because there's a reason why they show these dotted lines here. That's like implying there's a typical standard XY. So, and of course, it's pretty obvious it's 45 degrees here, actually. So the result will be correct in the end, but it's a lot of additional work for no reason because it's not needed as long as you have these, they are vectors. So as long as the vectors are in the same direction, well, why should I start to make them into my, let's call it artificial X, Y coordinate system, when I have a perfect coordinate system which says, well, that's the one in line with the two vectors. That's it. Then it's exactly what you said, right? That you can say P2 and P4 are equal. So that we have then P2, P4. So I don't have to consider any angle, which I could, and it would not be wrong. If I do it right, of course, the answer is correct, but it's just a lot of work for nothing. So that's a good approach. So then what is there for the, then of course it becomes very easy. What's the momentum of P2?
12 times V2.
Yep. So P2 and P4.
32 times 300.
Exactly. Just straightforward, actually, because it's vectors. So nobody forbids me to utilize the direction of these two vectors as opposites in this case, obviously, and don't have to, and I can use that as my coordinate system, so to speak. Okay. Then, of course, it becomes very clear. It's just actually ultimately rather on the easy side. The challenge is, of course, not the calculation, not this one, but to realize I don't have to go into my XY and then make 45-degree angles and I don't know what. Where, of course, in that moment, you go if you go into the XY, then of course the other ones become part of it. So then they are here as well, but then it becomes eventually pretty messy calculation. Of course, you can say, well, if they are opposite, they may eliminate itself. But how about if that? This is straightforward. That's the key. That's why this is a hard question, in order to realize it's actually simple, just by utilizing the vector direction of these two fragments. Okay, what about M3 now?
Same, just P3 equals P1.
Exactly. Same thing, exactly, and etc. Then of course, so we just have to solve it instead of we solve it for m. So in that regards, comparative, it's trivial then. Okay. So when you have to calculate n based upon the values we have, that's a bit different. That's why it's good to think about it. So both fireworks have the same initial mass and release the same amount of kinetic energy. So how should we go for that one?
I don't know what m is.
Okay. Then
Is it in the first one?
yes, sorry. Yes. So that's the two fireworks. That's a good point. So you have, I mean, this one is one firework and this one is one firework. And now by saying that both have the same kinetic energy, they're obviously having different values and of course different patterns. So this one explodes into 3, this one explodes into 4. But what we can see here is they have the same initial mass, as it was the same standard. The rockets weigh the same. Of course, it's wrong. We have to say rockets have the same mass when we launch them, and they will develop the same amount of kinetic energy. But their explosive pattern is a different one, however that is being achieved. But we still do not know yet the mass of the particles here. So now we want to know them based upon that additional information.
I think we just add up the mass of the fragments of the first one and then equal the sum of the second.
Exactly, huh? Yeah, that's good. So we say that, I mean, now of course it's whatever we can say, the masses of fireworks 1 are the same as the masses of fireworks 2, for example. Right? So that, I mean, it's more like a bit of a mind puzzle insofar, less of the direct physics, obviously in this question now. And what is now the sum of the masses for fireworks 1?
Just 9 over 2m.
Okay, yep. And this one, okay, I have to say what M3 was. Let me just, it's 26 grams.
I think it's 90.
Yeah, okay, yep, 90 grams. And then it becomes, again, right, it's basically all the questions A, B, C are, in terms of math, very simple in the end, because then we can figure out what M is. And of course, 9 divided by half, 4.5. So that's obviously 20 grams in consequence then for M. So just easy, right? But from the type of question and from the display of the various types here, it's something which we all have to realize. Oh, actually, just about the masses and they are equal. It's already stating it actually. So what do we probably have to do for B when we talk about the magnitude of B? What is the core to the answer here?
Um, I think we have to get the kinetic energy of each fraction.
Yeah, good one. Yeah, exactly right. So theoretically, of course, sometimes it's as well that we utilize the kinetic energy in order to get the mass. Okay, but in tendency, kinetic energy is usually quite often related to get the V out of it, so to speak. Right? So what you said, in other words, was that the kinetic energy of one is the kinetic energy of two. Actually, of course, it states it already here. So henceforth, of course, we can equalize them. And then we just have to set up painstakingly all the kinetic energy for each. So that is just like every mass multiplied with every square of the velocity on the one side with the first firework, do the same thing for the second firework. And if all is right, we should have in the meantime the mass for everything, right? So, and the velocities for everything. Then we can answer that question comparatively easy, right? Or in other words, strictly speaking, we don't even have to calculate the energy of the second one because by definition they are equal. But of course, it's a cross check if we got the values right, because if we do not get that equal, then we must have done something wrong in our calculation. It's just probably just a numeric value calculation error. So this is more like a cross check then, did we get it right? Because we want to know the magnitude of V, so we have the kinetic energy, of course, then we can just solve it accordingly based upon the kinetic energy in order to solve it for obviously still V, because we have not received either here. Here we have it. So here we calculated it. So obviously in this case we have all the values. So that's where kinetic energy 2 is completely can be calculated. Whereas this one has in two parts still a V left in order to make the calculation. So there comes the same thing all over again, that we have then the kinetic energy square, as for the kinetic energy of mv squared. And we have that, of course, then with the respective 0.6, 1.2, whatever. But in both cases, we have the V squared and we add them up because we add up the kinetic energy, right? So it's the same as what we said with the cost. Then you can just take the V squared to the front and then solve it for everything else, huh? Is that okay, Chris?
Yeah.
So it's basically just basically it's a bit more math than physics to a high degree because you just apply the formula. That of course it's a physical formula, but it's less physical thinking to some degree, and then you just have to solve that equation system for the one unknown, which is the V. But it's a bit more complicated because you have products and you have the sum of the unknowns, V plus V, so V squared, whatever, from one particle and the other. Then you have to solve it for that. Okay. If you look at 1E, let me just see. Yeah, I think we still do that because it's one of those ratio questions and they're always a bit, okay, what do I do in order to work with these ratios? We can see that, yes, the marks are high, but we can just apply our standard thinking again. So where would you start, Chris, when you look at what we have to show
Where is M1?
I know what you mean. Because here M1 is, of course, it has a value, but it's still M1. So because here they want to show the ratio. Like here when you have V4, for example, that's 500 meters per second, right? So they say the ratio of mass 1 to mass 2 is the same as the ratio of velocity 3 to velocity 4. It's why is like that is basically we have to get we find a way in order to say that. So in other words, the ratio of the masses, but I mean, on this side and that side is actually the same ratio as the velocity of this one and the 3 and the 4. So this one and that one. So the ratio of mass 1 to mass 2 is the same as the ratio of 3 to 4 velocity, or in other words, the mass of 3 to 4 or is then the same as the velocity of 1 to 4. Seems a very odd relationship, kind of not necessarily so logic, right? That you can say, well, basically the left-hand side is equal to the right-hand side, kind of, but in terms of ratio of the mass to ratio of the velocity. So that's what it basically says here. That may be interesting for certain calculations, of which we are not going into it here actually. And now what we have to do is we have show that is actually you have to calculate that so that we end up with that result. And how can we probably start?
Are we allowed to? Wait. Huh.
This is like what we said before, which momentums are the same? That's maybe a starting point.
1 and 3 and 2 and
okay, yeah. So P1 is P3, P2 is P4. Huh? Exactly. So that's it. That's one starting point. And of course, we can express our momentums then according with our m times v, where we obviously then have the whole m1, m1, p2, m2, v2, p3, oops, sorry, p3, m3, v3, p4, m4, v4. Huh? Just, I mean, it's obvious, but it still helps probably at some point to go into it. So, okay, so we have on one side a relationship established, which I can detail a bit more with the m and the v, which I probably have to do in order to end up on something like that. But it's probably not enough. That's a bit the tricky part here now. So what else could I bring in order to have a certain relationship? When you look at it and say, what is basically being created? So right now we looked at the same direction, huh? P1, P2, P4, P1, P3. And obviously it plays with symmetries. And of course, we have to get a bit of inspiration from this one to think of a symmetry. What could be a symmetry? Now think of these lines not as x, y, so to speak, but more as axis of symmetry. So which one could be eventually helpful? it's a bit playing around, or yeah, kind of as in a positive sense of playing. When you look at that axis of symmetry, what is then equal in terms of momentums?
The momentum on 1 plus 2 equals 4 plus 3.
Yeah, exactly. Yep. Very good. So it's a bit, yeah, well, you really have to see it at some point, right? And that's why when saying, okay, because the center stays, if it would not be symmetrical, the center of the fireworks would start moving either up or down, left or right, or all together actually. But it's not. Hence, it must be in equilibrium. And the beauty is, usually we think of forces in equilibrium, but of course, for momentum, it's the same thing actually. So the conservation of momentum is not just before or after per se, it's as well an equilibrium of the momentum itself at that moment they're existing, so to speak, like in this situation. So as we said, okay, then what is probably another symmetry I can apply?
4 plus 1 equals 3 plus 2.
Yo. Well, okay, huh? So now I have a ton of relationships. When I now look at the, yes, we started with this one. Let's see what we're going to do with this one. But when I look at that one, so they're all equal. So what can I ultimately say? When you look at these equations, P1 is P1 and P2 are equal to P3 to P4. P1 and P4 is equal to P2 to P3. It needs a little jump in thinking now, Chris, that you can say the next step. What could you make with these two relationships? Especially given the situation you have here in front of you, right? But when it's like when we sometimes we say it's equal 0, right? Before or after, or in this case, because these ratios, what is the value of this ratio? Is it variable or not? The value you get here, the result of that ratio, is it a variable or is it not variable?
It is.
Is 3 divided by 5 changing ever?
No.
Exactly. I mean, I know what you mean, right? So this is actually the breakthrough here is to say, well, it's a constant. It's constant. So that's why the ratios are always so well liked, because you put something in relation to the other, also into a ratio, and then you can say, well, that's constant because it has to be, right? So like here, if I put that into a relationship, there will be a constant value. What value is first, secondary? That's not so important at the moment. The key point is it's constant. So of course I can say the same thing here because that one is constant. P1 and P2 is, so that one is constant. And in the end, ultimately, I can say, well, they're all the same. Also, in other words, you could say P1 plus P2 is P3 plus P4, nothing new. But now I can say, well, but of course, it's the same as P1 plus P4. It's the same as P2 plus P3 is constant. Otherwise, I can't say this one. So that's why I say this is a bit of a jump to realize, well, typically we are more used to products, like for moment P, so the momentum MV, M1 times MV1 is equal to this one. We are a bit more used to products, but you can do the same for sums, of course, right? and say if they are equal, of course, then it's constant, no matter, it must be, otherwise it's not the same. If you have a different value here, so in other words, if you would have 0.6 as a result and 0.8, that's obviously not true. So it must be the same value in order to be true, to be equal, which means it must be the same value, which means it's a constant. It can only be one specific value, which is a constant, actually. I may vary my values here, but they must be as such that they will always result in the same value again. Of course, depending on what I choose for P1, P2, P3, P4, it will be a different value in the end. Maybe instead of 0.2, it may be 0.8. But it will always be a constant, which is always left side equal to right side. Otherwise, it can't be equal. You know? And that's when I can say it's a constant. Then, of course, I can say, well, then it must be a complete chain, so to speak, that they're all constant. Otherwise, it won't work because P1 shows up here, P2, P3, P4. It's just a different arrangement, but they're still the same four components. So that must be constant as well, and it must be equal to that. Otherwise, I can't get that result. So in other words, it's basically nothing else but a rearrangement. Then I get the same values, hence the constant. Is that so far okay, Chris?
Yeah.
So and now we of course need to come to a certain value, which in the end proves our point. It's a long exercise, and you have to go into the values as well. From the considerations, when you look at the first one again, what could you say from that one?
Which one?
Sorry, from the first one.
Oh.
So you must have something similar there, right?
Maybe 1 over P1 over P3 equals P2 over P4.
Yeah, we could go that way. Yes. Now the trick here is to say with, okay, in which direction am I heading, right? So eventually to get some ideas of what I would like to have. So of course, if I have here M1 and M2, it's probably helpful to think about the ratio of P1 to P2, for example. So what you would like to do is, for example, you can say, well, P1 over P2, no? Well, let's take what you said, is, for example, so we divide it by P2 is the same as what could you say here, Chris?
P3 over P4. Right.
Is that which is P3 over P4, right? Is that what you said?
P3 over P4.
Okay, yep. Okay, so that's one way, but something we can say. So, as a result of this one, and then of course we can apply P1, obviously, and P4. What can we then? What is then another? And well, basically we can take it like that. So we have that relationship. Of course, now I'd say the step ultimately is in order to say, well, I can make the ratio, or in other words, when I take that one, let's take that as 1, for example. Of course, I can make then 1 into M1, say M1 P1 over M2 P2. Equals to M3 V3 to so we have basically 1 extended into this equation. Now the point is, of course, that should be a 2, excuse me. I think, Chris, what I suggest is, you know what, it will take quite a long time now to go with that one. It's a bit, and I will really look at the question now. I think we are using our time. It's an interesting question, but it has a lot to do with math and relationships. So from a physics point of view, because what we would do next is then to come with the second relationship, so to speak, which is just to very briefly show you that is, I can as well say M1 over V1 over M4 over V4 is equal to M3 over V3 divided by M2 over V2. I could use that as the second one. From the same set, I just do a different division in order to get the second set of equations. Which I have at my disposition, so to speak. And what I can do is then, on one side, I want to prove of this step here. Let's say this one M1 over M3 over M4, M1 over M4. This one, I can separate basically the numbers and put the ratios into each other. That's my point, right? So in other words, what I can do is M1 over M4 times V1 over V4 is M3 over M2 times V3 over V2. So you basically separate them into ratios on their own. And because we have the values, we can, of course, identify the respective values. So I have, because I can, because we have, in other words, we utilize the values of the momentum and can get therefore the ratio of what is respectively in connection with each other. And this is about something we have not calculated, but we can say there are two things we have to consider. This is momentum 1. So we have to so we can calculate that momentum. We have a value for that. And what I can say is then if I really do that, I have a momentum, which is the first one is 6/15. So M1 times, also P1 is 6/15, which is then, of course, for the P3, which is 2/5. I mean, you could just calculate it, just M times V. So basically, just do the calculation with the values. Then we have that. And then I can actually put the values in ratio to each other. V3 to V2. Because what I can show as well is relationship of proportions between the mass and the velocity. So the next step, apart from getting the momentum, like what we've done here, is then as well that you can put these masses and velocities into proportion to each other, according to what we are interested in. So, and then I can simplify that in order to make the ratios accordingly. Is that something which you see, Chris? This is okay. What I will do, Chris, is the following. This is something which is I will write it down to you and send you the solution. Huh?
Okay.
I think that's better. That's better because it gets. Otherwise, we just go on, and it's easier if I can show it to you there, because it really is something which is maybe something we can follow up eventually. But I send you the solution first. You may have a look at it, and then we discuss it. Huh? I think that's the better approach now. We come to some point, but from then onwards, from here onwards, it has a couple of things involved, which will still take quite some time to explain it. We can see here we have the moments. So this is what we calculate here, the momentum as a result of the values. So we can therefore put those ratios times and the product of the ratios have a certain value. And in the end, I mean, obviously, I need to put that somewhere in the end into this relationship that I have ultimately N1 over N2. Basically, N1 over N2 is the same as V3 over V4. So that means we have to do something with this one and we have to do something with this one in order to come up with that one. Then utilize this situation as well. That is something I rather show you then in the solution. Huh? So I think in order to close it for today, we do this one as a kind of standard question. when you have a block which is suspended here. And a bullet or a pellet hits it. And then, of course, it gets pushed out of the way. And we have to determine the velocity. And it's given as well that we say it's the height, it's pushed up, so to speak, or the center of the is moving up from here to here. So in a vertical position, in a vertical situation, it moves h up. So the center of the mass. That's something which is obviously helpful. So when we look at that diagram, we have, say, this one. It has a length, right? So let's just call that L. Because it's swinging, so of course this one still has a length of L. And how can we now determine the height? Because we need the height. How do we calculate A, John?
I think we use tangent. Because oh no.
Yep, it's actually straightforward in that regards. So we have the from the to the center of the block. Maybe I have to that was a bit misleading. So center of the block. That may help you now because that was a bit misleading how I draw it. So when you look at it here, what can you say in order to get H? It's straightforward, Chris. It's not too complicated. Exactly.
Use because we know G cosine is
yep.
The 1.5 cosine 35 degrees.
And what is L? So when you look at this length here, that's to the center. Huh? So this length is now this one. I mean, sorry, this one, because that's your cosine, right? Up to here. As up to here. My bad. Excuse me. So because the length is up to here. Huh? So this is your cosine now. This is your L cos 35, right? This is the length.
Yeah. Well, L cosine 35 equals 1.5.
Something's missing, because it's a bit a tricky part. I mean, the drawing is, frankly speaking, is a bit nasty, because in the text it says a string measured from the pivot to the center of the block. So pivot point is here, is here. Center of the block is here or here, here or here. That is the center of the block, right? Am I correct, Chris?
Yeah.
But the drawing doesn't show it, so that's a bit nasty. That's what I mean by nasty part, because actually your length goes up to here. Same here, so that length is the same and goes up to here. That enables you to actually say, well, that one, that section here is your L cos. Okay, that looks a bit nasty. This is your L cos. Excuse me. Your L cos 35. That's your red part up to here. Huh? This is L as well, to the center. So L times cos 35 is your red part, is this one. But your L, actually, as you can see, goes all the way down. So what do you have to add to this part in order to make it equal to this?
L minus that.
What about H when you look at it?
L minus
Okay, yeah, okay, okay, I know what you mean. Yes, could say it like that. I would have said, well, it's fine. I would have said L is plus H. So in other words, because this is H as well, right?
Oh, yeah.
Right, so you basically take, or make it in red, so to speak, plus H, sorry, or orange. So we have this one. So then, of course, the red and the orange together are the green, so to speak. Huh? So it has to do a bit with this cos sign thinking, or in other words, what this one plays with is this, and this is the radius, so our L. So of course, it makes such a curve, which means when you are at a certain angle, let's take the green one. So this is my L, of course. L is everywhere the same. So, and now my cos, of course, is exactly this one, right? Where you have the projection down, depending on the angle theta. So I have this one. So what is always missing is the flexible, if you want to say so. This delta here is always, of course, is growing as your cos is shrinking, so to speak. The higher up it is, of course, the less the cos, and the bigger that difference here, which we are usually not interested. We are usually interested in this one, or of course in the sine, that's for sure. And this one is then just, yeah, of course, it's the difference to what we have in the sine. But in this case now, it's just, yeah, it's exactly that missing part of our circle as the, I mean, better said here, as it goes like that. So of course, then that if I project now my L back to this one with the 35 angle, I have the L cos, and then this is the missing part, which is the height. Right? So we get this one. So obviously now I can call, or you say it's the L minus the H is equal to this one. That of course is fine as well, of course. So henceforth I can just say L minus L cos 35 is my H. Huh? So I have that one already figured out. So I get now comes fitting. That was kind of more math trigonometry kind of. Now how can I find the velocity? So this one is now something which has less to do with what we discussed before. In other words, when you think, so if you do not think momentum and not forces, first of all, what else do we then can we consider as well in order to make such calculation, Chris? So conservation of momentum is one. What is the other one we usually apply as well?
The energy.
Yeah, exactly. And in this case now, because this is important, this is the final position. It will not swing further up. It will stop, and of course, as a pendulum, ultimately return. So at this point here, and at this point here, what is the? It will be hit, right? So it will be hit by the pellet at that moment. So a fraction of a second later, at first it's of course at rest. That's sometimes a bit difficult to wrap your head around, but a tiny little second, slightly move, but not really. And in terms of our considerations, we still look at it as like this. But what type of energy will it have here already as a result of the impact of the pellet?
Kinetic.
Exactly, huh? So we can say here, so and therefore, and what type of energy will it have here?
Gravitational potential energy.
Exactly, because of course, strictly speaking, we always say, of course, kinetic energy plus potential energy. Usually write it as a K and GP. Let's make it proper in terms of kinetic energy and potential energy of before is the same as afterwards, huh? GP, right? 1, 1, 2, 2. And of course, this one, relatively speaking, the potential energy, relatively speaking, here is 0. Of course, it has its own, but so does this one. So we can eliminate that part of the potential energy. So the difference counts. And of course, the other way around, as it's the final position, no kinetic energy, right? So hence, we can come up with that conclusion. That's, of course, the key equation always counts. It's always the sum of potential and kinetic. Usually, of course, you can have other ones, but usually we look at kinetic and potential. The sum of the two are equal, but usually one is 0 in before and after. Then we can equalize that. And if we put it equal, of course, we can say, well, this is, of course, v squared and m times g times h. Huh? So what can I do with that equation now, Chris?
So the height times the combined mass times 9.81 equals to the 1/2 times the pellet mass times its velocity squared.
Is it the pellet mass or is it the block mass?
Oh, wait. Oh, it's both the pellet and the block.
If you would look at momentum, yes, but you are not interested in momentum anymore, right? So yeah, or what you can say is, well, it combined or not. Yes, okay. Let's say wait, I change it here. It's better to make it sure we talk about the combined one, huh? Okay, because it's a system of both. But what can you see from that equation? Does it even matter?
Oh, it doesn't.
Exactly, right? In light of what we want to calculate, because we want to have v squared solved. So that's what we don't know. So hence we can as well eliminate because left and right. So that's the funny thing, actually. Yes, you are completely right. You have to include that one. But of course, this one now what? So, but of course, in terms of the of the system, and does it say that? Yes, completely embedded. So that's the one where we can safely say it's a new mass being formed, so to speak, of the total. It moves up as well. Could as well be that it's not, but then it would be a different question. Exactly. And then if you rearrange that, then of course we have nothing else but it's a very classic formula actually. this one. The velocity is the result of the height. It has been moved up, double the height. We may say that, times, of course, the gravitational force factor, g, and of course the square root out of it. So it's completely independent of the mass. It's only driven, of course, by, of course, as you talk about potential energy, you talk about this one. So in other words, how either the velocity has to come in order to result in that, or you go the other way around and say how high it goes up depends then on the velocity, right? You can rearrange it as well, in other words. Could go for height depending on the v it arrives, which is kind of obvious. The more v you have, the higher momentum you have, the higher up it will go. So that's the relationship between the two. So you will have to calculate that more than once, actually, in various type of questions. So it's a pretty standard one. Okay. Then we'll do next Friday again, and I will send you in the meantime for the other, which is less physics, but a lot of more like logical rearrangement of certain relationships, which is interesting to see nevertheless. Okay, and like we discussed, we will deal with the measurement, also the significant figures and the error measurements as well, for calculations. Okay, all right, have a good week, Chris.
Yeah, you too.
Thank you. Bye.
Okay, bye. Oh my God. Podcast. New podcast. Let's make a podcast. Everyone needs their own podcast. I'm sick and tired. Being by the biggest hater. What the hell happened? Oh, I suppose the community. There's always people I dislike. Imagine yourself in a classroom of 20. And then those 17 are supporting you 3 are distraught. Basically, I don't get to get any recording because my other recording corrupt.